Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Magic Micromodules with Adaptive Switching All-in-One Solution for the Industrial Sector. Our referent for this session is Timur Uludag. He will hold the presentation and will answer your questions. But before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation, but nevertheless, you have the opportunity to ask questions during the presentation at any time via the question window. And you can find the question window in the webinar control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are about 5 to 10 minutes in addition scheduled for this. And if we are unable to answer all of your questions within this time, we will answer them via email afterwards. And if you still have any other questions left, just mail us at exhibition@we-online.com. And we will, of course, try to answer all of your questions promptly. At the end of the presentation, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will also receive the link to the presentation in the next few days, and the recording will be available at our website shortly. But now I would say it's time for our speaker Timur, and I wish you an exciting presentation.
So thank you, Marie, for this small introduction, and thank you for joining my webinar today. So the next, let's say 30 minutes, we will take a look on our micromodules with adaptive switching and how it fulfills the requirements of a typical industrial application. First of all, it's all about the applications. The application gives us the boundary conditions in which the DC-DC must operate. Derived from the application, the requirements for the DC-DC and its switching behavior are as followed. In addition to the pure switching behavior, features are also very necessary to fulfill the requirements arising from the industrial applications. The layout approach section shows the benefits of an optimized layout for the application. The conclusion section will summarize the properties of the BDMMs or micromodules to fulfill the given requirements. Our more than you expect values will show that Magic Power Modules is way more than pure hardware. As a starting point now, we need to understand the environment of our DC-DC to know what requirements we have here. Easiest way to get the understanding is to look at an example application. Let's check it out. A typical industrial application structure could look like this. We have here a surveillance camera that is installed in various positions that often do not have a direct connection to the DC bus and have very limited installation space. This is what we call here our System 1. Industrial-grade inductive sensors are usually connected directly to the DC bus. This is our System 2 here, as you can see. Their design is similar to a matrix screw, let's say a M12, in which the sensor and the evaluation electronics are integrated. The described applications have here all one in common. They are so-called space constrained. But what does space constraint mean for DC-DC? What challenges for the DC-DC converters can be derived from the structure that was described in the slide before. To get a better understanding, we take a look what the different applications have in common here for the requirements of a DC-DC and what is special, bus specific for 5 volts, 24 volts. Space constraint comes with a need of restricted board space, which can be solved by tiny solution size of the DC-DC. Less space for integration also means there is no space for additional cooling. Ideally speaking, the DC-DC should have nearly a minimum self-heating. So let's say it has to stay cool. Industrial DC buses, like the 24 volt, is not tightly regulated in a very big industrial environment like logistics or warehouses. It has tolerances that are mostly undesirable. The DC-DC should be robust to handle these input voltage fluctuations. There are mainly two standards that describe the voltage tolerances of the DC-DC bus voltage. First, we have got the PLC standard, the IEC 61131-2. It describes the input voltage range from 15.5 to 30 volts. The highest tolerance for the 24 volt bus you can find is described in the rolling stock standard, the EN 50155. Here we have got a huge range from 14.4 up to 33.6 volts. But both standards do not really describe the reality. Various factors play here a critical role in how much the 24 volts deviates from the tolerance ranges we have seen now. For example, if the 24 volt bus supply line is laid parallel to the control line of a frequency inverter, and the frequency inverter is pulsing, then if we have a capacitively coupled effect, then the 24 volt oscillates in the same pulse pattern as a frequency inverter. On the other hand, with a minimum input voltage of 3.4 volts, the 5 volt bus with its plus minus 10% variation can easily be covered. After looking now on the bus supply, let's dive into the converter behavior. What could be important with the way of functioning, and what role does the topology play with that? Here we have a, let's say, typical basic principled structure. We have got here our supply, our DC-DC, the power module, and the load here. If we look, let's say, for a measurement application, there will be a higher current demand for measuring and a lower one between the measurement points. Therefore, the power management has to be flexible enough to have the best performance for each load situation. That means for light load and for nominal load. The slide here is very essential to understand. This slide shows the efficiency diagram of our 0.3 amp micromodule as an example for the different load situations. This is here the efficiency curve of our VDM amp. The black graph we can see is the typical behavior as we know from standard buck converters. You can see it starts here and rises up smoothly. The PWM mode is widely used, and you can find this principle in AC/DC general power supplies also. This works fine for these kinds of applications as they work in nearly full load conditions all the time. But applications like sensors are different here. Here, the light load condition is the predominant operating mode. Therefore, the switching behavior has to be modified for this load situation. In contrast to the PWM mode, the PFM mode, we have here the red graph, shows a wider efficiency plateau as the light load area. Here you can see it's nearly constant. In contrast to the PWM mode, that is here in black, you can see it is rising, and here you have got only a small plateau where you have a constant efficiency. To have a very good efficiency supports longer lifetime of a battery, let's say in a portable device. To better show the effect of PFM and PWM mode in light load, I placed both curves in one graph. Now the big difference of the PFM and PWM mode efficiency curves is more pronounced. As you can see, we will rise up here very quickly to over 80% at 10 milliamps. And if you see in contrast here the PWM mode, it's rising very slow, and we have got only here 25%. So at 10 milliamps, we have got a difference of 65%, where the PFM mode has more efficiency. To show the importance of the efficiency more clearly, what it really means for a device that is supplying something, I placed the thermal derating curve of the VDMM power module, the red graph, and the black one for the LDO in one graph. As you can see here, based on the good efficiency of over 80%, you can get from -40 up to 95 degrees C full load, 0.3 amps. In contrast here, the LDO, where you can see the derating starts at -40 degrees and goes down to, let's say, 5 milliamps. But why is there such a huge difference in the behavior for the thermal derating? The next slide will explain this more clearly. If we can compare now the DC-DC with LDO, then you will see that every watt that is not used for supplying, that is transferred to heat, will negatively influence the performance of the supply. If we take a look on the LDO, then you will see that only 20% of the input power is used for the applications. In contrast here, over 80% here is used to supply the application. The remaining 80% of the LDO will be transferred in pure heat generation, what negatively affects the derating. To make it, let's say, more clear, I make a small numerical example here. What it means if we can, let's say, push our efficiency for the lifetime of a standard 2800 milliamp hours battery. If we see that we have, let's say, 10 milliamps, and we calculate an efficiency of 20%, what we have for an LDO, and we go up to 85%, which we have nearly for our DC-DC converters, then you can see that we have got a difference in over 400% in lifetime between an LDO and the power module. For me, this is significant. But how it comes? Let me explain you a little bit more about PWM and PFM mode. PWM mode is characterized by constant switching behavior, and therefore constant switching means constant losses. In PFM operation, the high side switch here is turned off. That means the switching stops. No switching, no losses. During the time between the high side switch turned off and the high side switch turned on, the load is only supplied by the output capacitor. The output capacitor discharges, which leads to a voltage drop. The high side switch is then turned on again when the output voltage drops below an internal threshold. Turns on again, turns off. Here you can see the voltage drop of the output capacitor until a value is reached that kicks in the process again. Each mode of operation here has its own pros and cons. For example, the PFM mode can achieve the advanced of improving the light load efficiency, here in green, but at the cost of introducing relatively high output voltage ripple, here in red. In case it is desired to reduce these ripples, the output capacitor of the module should be increased. On the other hand, PWM mode has the advantages of fixed switching frequency and low output voltage ripple, while having relatively low light load efficiency. Low output voltage ripple, low efficiency. The new VDMM here brings the best of both worlds together, as it improves the light load efficiency while keeping the output voltage ripples low and omit the need to increase the output capacitor and hence expanding the solution size. That means we take the red ones from the PFM mode and the red ones from the PWM mode and mix it together in one module and make all green. So the best of both worlds. So, as teased at the beginning, not only basic parameters like the input voltage or efficiency are of interest. The converter should also provide a diverse function set. Let's have a look at those important ones. First, the enable function. Inherently, the enable function sets the DC-DC converter to start routine when a specific threshold is reached. After setting enable high, the DC-DC converter prepares for operation, a process that takes roughly some microseconds for this special micromodule. Once prepared, the module begins switching, and the internal soft start regulates the output voltage rise and until the desired output voltage is met, allowing normal operating to take place. Second feature, the power good feature. Once the output voltage is above 90% of the internal reference voltage, the power good pin transitions to a high impedance state. The power good pin is pulled low when the output voltage is lower than 95% or higher than 105% of the internal reference voltage. If we now take on the one hand the enable function and on the other one the power good and mix it together, then we can make something that is called power supply sequencing. Each module's power good signal acts as the enable signal for the following one module, turning them on in a cascading sequence. Means here the power good pin goes into the enable pin of the second module and is enabling it. Or here the power good is going to the third module and is enabling it. So from written theory on paper, we discovered deeply our given application requirements, but haven't spoken about how to implement. I guess now it's a good time to talk about a real optimized layout and what aspects should be considered. To realize the VDMM on a PCB, only 66 millimeters squared is needed. The PCB design here is very simple. Only one top and one bottom layer is sufficient. The red bordered area shows the solution size with its essential parts to get the VDMM up and running. This here, this red line. But what does 66 millimeters squared mean? Let me try to make this value a little bit more tangible. Remember again, the area of the solution size is 66 millimeters squared. If we compare this to our well-known MagI in a 5030 package, then you can see that the solution size is only 2 times bigger. But here we're talking about 5.4 by 5.4 millimeters. If we compare this solution size with a 1 euro cent coin, then you will see that our solution size is 3 times smaller. Last but not least, if we take a CR2032 coin cell battery you can use for your carports or some other devices, then you will see that our solution size is 4.5 times smaller. So 66 millimeters squared to realize the whole module and its essential components. That's pretty tiny for me. Let's take a look on the thermal behavior. If we go on Red Expert and then select the thermal prediction module we have here for our modules, then you will see if we go for a ratio of 24 volts down to 5 volts at nominal load 0.3 amps, and we put in a value like 300 milliwatts as the losses and refer to an 80 by 80 millimeter surface, then you can see that we have only a hotspot temperature of 41 degrees. So that's very, very cool. And again, this is only a PCB with one top and one bottom layer and only 35 micrometers copper. It will be, let's say, more visible if we increase the losses. Now I increase the losses to 400 milliwatts. Same layout, the same environment, and we see that we only have here a hotspot temperature of 46 degrees C. That means 100 milliwatts more means only 5 Kelvin more in temperature rise. So this is for me a very cool device. But switching current loops that act as antennas are the source for radiated emissions, and we will always have them. But due to the tiny solution size of the module, the affected antenna structure could be minimized. In, let's say, orange-yellow, you can see this is the input current switching loop, and this is the output switching current loop. And if you keep in mind, this is the solution size, and here we're talking only about 66 millimeters squared. So the surface here for the antennas is very, very, very low. This module passes the EN 55032 with the need of only a minimum external filter. So the margin to the limit here is huge. We have nearly 20 dBs over the whole frequency range for the radiated emission. As you can see here, there is a huge margin we have. We now spent some time and discovered a lot about application requirements and implementation consideration. Next, let's see all these information in a nutshell. The micromodule we have presented here can fulfill all the requirements that comes from a typical industrial application. We have got the ultra-wide input voltage range. We have got a huge operating ambient temperature range that is beyond the normal industrial one that goes up to 85 degrees only. We have got a very low profile because we're using an AGA package. So it is perfectly fitted for all space constrained applications. To round the design in of the power module off, we have our more than you expect services. That means more than you expect is way more than pure hardware on your PCB. We can support you in any way you can think of to realize your design in. We can help you by the beginning with the design in support of the pure hardware. We can follow up with you on the EMC design support. We can put all this together and make a layout review. And last but not least, the thermal aspect is also something we can help you a lot. We can help you with our Red Expert prediction tool for the thermal behavior, or we can do it individually with your custom design. So I think you enjoyed the show. If you have more questions that are, let's say, beyond the time we have now here, then please contact us. We have got our hotline, and we have got 3 guys there who are here to help you. So thank you. And I'm staying here and waiting for your questions.
Thank you so much, Timur. Yeah,
Welcome.
as you already mentioned, you have now time to enter your questions into the question window. So feel free to ask all of your questions. Timur, I would say let's start with the first one. Is the 36 volt the max transient voltage?
No. This is the normal operating range we have. We can go up to 38 volts in transient behavior. So we have got a little bit more there, a little bit of overhead we have here.
Okay, great. Thanks. Another question, why do we have an operating temperature range up to 105 degrees?
Good question, good question. This is because the normal, let's say, operating temperature range in industrial applications is from -40 up to 85 degrees. But if you want to go for sensors, then these sensors, like I mentioned, this inductive sensor is placed in, let's say, hotter air areas where you can reach very, very easily this 85 degrees. And to have here more margin for the application, to have it more for the customer, we have spent some degrees more, so you can have it up to 95 degrees without any derating. And you can go up to 105 degrees with a small derating. So more than you get for this.
Okay, thanks for the explanation, Timur. Another question is coming in. Why is there only a 300 milliampere version available?
This is because a typical application like an FPGA, the IOs, there is only the need of some milliamps here to cover more application. We enlarged it from some milliamps to 300 milliamps because this is a suitable value to cover a lot of applications in this special field.
Okay, great. Thanks. I would say if there are any questions left, just as Timur said, you can gladly ask the colleagues or also write us an email to exhibition@we-online.com. And you will also receive the link to the presentation via email in the next few days, and also the recording will be available at our website this week. Let me show you what's coming next today. We still have one presentation for today from Pablo Castillo and Carlos Farnos with the topic flat wire inductors for electrical cars. So see you there at 4 p.m. and have a nice day. Thanks, Timur, and goodbye.
Thank you. Bye.